Hello there! Tonight we are drifting gently into one of the most quietly fascinating subjects in the whole of human experience. The possibility that we are not alone. The long, strange history of what people have seen in the sky and described across every era of recorded time, the serious scientific search for life beyond Earth, and the genuine discoveries that are slowly, carefully reshaping what we thought we knew about the universe and our place in it. This is not a frightening subject, it is a wonder-filled one. The sky above you right now is ancient and vast and full of things we are only beginning to understand, and tonight we are going to drift through that vastness together, through sightings and signals and deep space observations and the careful, patient work of astronomers and biologists who spend their careers asking whether life on Earth is a fluke or a rule. Before we begin, take a moment to subscribe and like the video, and leave a comment telling me where you are listening from and what time it is for you. Now let's begin. Start with the numbers, because the numbers are the first reason that the question of life beyond Earth has moved from the fringes of science to its very center. There are approximately 2 trillion galaxies in the observable universe. Each galaxy contains, on average, somewhere between 100 billion and 1 trillion stars. Our own galaxy, the Milky Way, is estimated to contain between 100 and 400 billion stars. And we now know from the Kepler Space Telescope and its successors that most stars have planets. The estimate runs to approximately 1 planet per star on average, meaning there are more planets in the Milky Way alone than there are stars. Of those planets, a significant fraction orbit in the habitable zone, the range of distances from a star where liquid water could exist on a rocky surface. Conservative estimates place the number of potentially habitable planets in the Milky Way at somewhere between 10 billion and 40 billion. These are not exotic estimates from the fringes of astronomy. They are the mainstream consensus of planetary science in 2024. The question of whether life exists elsewhere is, at its foundation, a question about whether chemistry that assembled itself into life on one of roughly 40 billion suitable planets in one of 2 trillion galaxies somehow represented a one-time accident that never repeated. This is what serious scientists are trying to determine, and the answer is not yet known. The Drake equation, written down by the astronomer Frank Drake in 1961 before a gathering of scientists at the Green Bank Observatory in West Virginia, was not an answer. It was a framework, a way of organizing the question of how many communicating civilizations might exist in our galaxy right now. The equation multiplies together a series of factors: the rate at which new stars form in the galaxy, the fraction of those stars with planets, the fraction of planets that could support life, the fraction on which life actually develops, the fraction of those where life develops intelligence, the fraction of intelligent species that develop technology capable of interstellar communication, and the length of time such civilizations broadcast detectable signals. Drake wrote it on a blackboard in 1961 as a way of structuring the agenda for the meeting. What he probably did not anticipate was that the equation would be discussed, debated, and refined for the next 60 years and become one of the most famous expressions in the history of science. The equation's value depends entirely on the values you assign to each factor, most of which were unknown in 1961 and several of which remain deeply uncertain today. The first 2 factors, the rate of star formation and the fraction with planets, are now reasonably well constrained by observation. The biological and civilizational factors remain almost entirely speculative, but the framework itself, the act of breaking the question into tractable pieces, was itself a scientific contribution of lasting value. The search for extraterrestrial intelligence, SETI, has been running in various forms since the early 1960s, when Frank Drake himself pointed the 85-foot Taytel telescope at 2 nearby sun-like stars and listened for radio signals in a project he called Project Ozma, named after the ruler of the land of Oz. In the 6 hours of observing time he managed to secure, Drake detected nothing unusual. But the project established a methodology. Point a sensitive radio receiver at stars that might harbor inhabited planets, listen at frequencies where physics suggests interstellar communication would be efficient, and look for signals that show the hallmarks of intelligent origin: regularity, information content, or structures that natural processes would not produce. This methodology has been refined and expanded enormously over the 60 years since OSMA, with larger telescopes, wider frequency coverage, more sophisticated signal processing, and the ability to monitor many millions of frequency channels simultaneously. The SETI Institute, founded in 1984, coordinates much of this work, and the Allen Telescope Array in Northern California was built specifically for SETI observations. In recent years, the Breakthrough Listen initiative, funded by billionaire Yuri Milner with $100 million, has brought the most comprehensive SETI program yet to life, using some of the world's largest telescopes to survey 1 million nearby stars and 100 nearby galaxies across a wide range of frequencies. After 60 years of listening, we have heard no confirmed signal from another civilization, but we have also only listened to a tiny fraction of the sky for a tiny fraction of the time, across a tiny fraction of the possible frequencies and signal types. The search continues. The most famous moment in the history of SETI came on August 15, 1977, when a volunteer astronomer named Jerry Amon was reviewing computer printouts of radio data collected by the Big Ear telescope at Ohio State University. Big Ear was not a traditional dish telescope but a flat reflector the size of 3 football fields, and it swept across the sky as the Earth rotated, spending approximately 72 seconds on each point it surveyed. As Eamon worked through the printouts, looking for signals that stood out from the background noise, he found a sequence of characters that represented a signal of remarkable intensity and exactly the kind of characteristics that a beacon from another civilization might display. The signal appeared at 1420 MHz. The hydrogen line frequency, which SETI pioneers had suggested decades earlier, would be a natural choice for interstellar communication, because hydrogen is the most abundant element in the universe and its radio frequency is a universal physical constant. The signal lasted the full 72 seconds that the telescope spent pointing at that part of the sky, consistent with a real astronomical source rather than radio frequency interference. Eamon circled the sequence of characters on the printout and wrote in the margin a single word: "Wow." The wow signal, as it has been known ever since, has never been detected again despite many attempts. It has never been explained. It may have been a natural astronomical phenomenon of a type that has never been identified. It may have been terrestrial interference from an unknown source, or it may have been exactly what it appeared to be, a signal from somewhere else, in the right place, at the right frequency, lasting exactly as long as physics would predict for a real extraterrestrial source. We genuinely do not know. Radio is not the only way to search for signs of other civilizations. As our own technology has developed, astronomers have recognized that advanced civilizations might be detectable through a variety of signatures that they could not fully hide, even if they tried. Industrial civilizations alter their planet's atmospheres in detectable ways. The oxygen in Earth's atmosphere is largely a biological product and would appear in the spectrum of light from our planet as a biosignature. The combination of oxygen and methane simultaneously is particularly significant because these two gases react with each other and would only coexist in a planetary atmosphere if something were continuously replenishing them, the most plausible continuous source being biology. The search for these chemical biosignatures in the atmospheres of exoplanets is now possible in principle with the James Webb Space Telescope, launched in December 2021, and will become increasingly powerful as the next generation of extremely large ground-based telescopes comes into operation in the late 2020s and 2030s. Beyond chemistry, a sufficiently advanced civilization might be detectable by its engineering. Freeman Dyson proposed in 1960 that a civilization seeking to extract the maximum energy from its star might build a shell or a swarm of structures around it, a Dyson sphere, that would intercept stellar radiation and radiate it as waste heat in the infrared. Several searches for anomalous infrared sources have been conducted with this in mind, and the star KIC 8462852, nicknamed Tabby's star, produced a brief burst of excitement in 2015 when its brightness was found to dip irregularly by as much as 22%, far more than any known planetary transit could produce. The ultimate explanation appears to be unusual clouds of cometary dust rather than alien megastructures, but the brief possibility was taken seriously by scientists, which itself reflects the shift in how the scientific community thinks about this question. The discovery of exoplanets, planets orbiting stars other than our Sun, is one of the most transformative developments in the history of astronomy, and its speed has been remarkable. Before 1992, no confirmed exoplanet existed. The first confirmed detections, announced in 1992 and 1995, came through different methods and opened a floodgate. By the time the Kepler Space Telescope completed its primary mission in 2018, it had confirmed the existence of more than 2,600 exoplanets. The total confirmed exoplanet count across all detection methods and missions stands at well over 5,500 as of 2024, with many thousands more candidates awaiting confirmation. The diversity of this planetary census has been one of its most surprising features. Before exoplanet detection, astronomers assumed other solar systems would broadly resemble our own. They were wrong. Hot Jupiters, gas giant planets in orbits far closer to their stars than Mercury is to the Sun, turned out to be surprisingly common, at least in the sample detectable by early methods. Super-Earths, rocky planets larger than Earth but smaller than Neptune, with no equivalent in our solar system, turned out to be perhaps the most common type of planet in the galaxy. The architecture of other planetary systems is far more varied and strange than our own, which raises fascinating questions about whether the specific configuration of our solar system, with its small rocky inner planets and its large outer gas giants that may have shielded the inner planets from excessive bombardment, is typical, unusual, or necessary for the development of complex life. Among the thousands of known exoplanets, a special subset have attracted the most intense scrutiny. The rocky planets in the habitable zones of their stars, the world's most likely to harbor liquid water and potentially life. The TRAPPIST-1 system, announced in 2017, was a landmark discovery in this context. Around a dim red dwarf star approximately 40 light-years from Earth, astronomers found 7 planets, all roughly Earth-sized, 3 of which orbit in the habitable zone. The planets are so close to their small, cool star that their orbital periods are measured in days rather than years, and they are almost certainly tidally locked, keeping one face perpetually toward the star and one perpetually in darkness, the way our moon keeps one face toward Earth. This tidal locking was initially considered a problem for habitability because it was thought to produce extreme temperature gradients between the day and night sides, but more recent climate modeling suggests that atmospheres and oceans could moderate these gradients enough for habitable conditions to exist, particularly near the terminator line, the boundary between the permanent day and night sides. The TRAPPIST-1 planets are close enough to be studied in detail by the James Webb Space Telescope, and preliminary atmospheric observations have begun. The results so far are inconclusive, but are expected to improve significantly with additional observing time. TRAPPIST-1 may be the first system where we accumulate genuine evidence, one way or another, about the presence of a biosphere on another world. The moons of the outer solar system have become, over the last 2 decades, the most compelling candidates in the solar system for harboring life, not on their surfaces, which are frozen and inhospitable, but in vast subsurface oceans of liquid water kept warm by the gravitational friction of their parent planets. Europa, one of Jupiter's 4 large Galilean moons, was known to be geologically interesting from the Voyager flybys of the 1970s. When the Galileo spacecraft entered orbit around Jupiter in the 1990s and made repeated close passes of Europa, the evidence for a subsurface ocean became overwhelming. Europa's icy surface is covered in a network of reddish-brown cracks and ridges that show clear signs of having been deformed from below by liquid water. The slight wobble of Europa in its orbit is consistent with a conducting layer, most likely a saltwater ocean, beneath the ice. The ocean is estimated to be approximately 100 kilometers deep, containing more liquid water than all of Earth's oceans combined, and it is in contact with the rocky seafloor, where the gravitational tidal heating that keeps the water liquid would also be expected to drive hydrothermal venting, the same kind of environment found in the deep-sea hydrothermal vents of Earth's oceans, which support rich and diverse ecosystems powered entirely by chemical energy rather than sunlight. The NASA Europa Clipper mission, launched in October 2024, is on its way to study Europa in unprecedented detail, arriving at Jupiter in 2030. It will not land on Europa or drill through the ice, but its instruments will characterize the ocean's chemistry, the thickness and composition of the ice shell, and the potential for the exchange of material between the surface and the ocean below. Enceladus, one of Saturn's moons, has provided perhaps the most direct evidence of subsurface ocean chemistry anywhere in the solar system beyond Earth. In 2005, the Cassini spacecraft discovered that Enceladus is geologically active, with plumes of water vapor and ice particles erupting from a series of fractures near the Moon's south pole, the so-called tiger stripes. These plumes extend hundreds of kilometers into space and supply material to Saturn's E-ring. The discovery that Enceladus has ongoing water vapor activity was remarkable in itself. What made it transformative was what Cassini found when it flew directly through the plumes and analyzed their composition. The plumes contain water, sodium chloride, carbon dioxide, methane, molecular hydrogen, and a range of organic compounds, including several complex organic molecules. The presence of molecular hydrogen is particularly significant because it indicates that water is reacting with hot rock in hydrothermal systems at the seafloor, a process called serpentinization that on Earth is associated with chemosynthetic ecosystems that do not require sunlight. The chemical energy available from this reaction could, in principle, support microbial life. The Enceladus Ocean is actively communicating with its rocky floor, being kept warm by tidal heating, and sending plumes of its chemistry directly into space where a passing spacecraft can sample them without landing. If there is microbial life in the Enceladus Ocean, its chemical signatures may already be present in the Cassini data, waiting to be identified. Titan, Saturn's largest moon, is often discussed in the context of the search for life for a different reason. Its surface, at -179 degrees Celsius, is far too cold for liquid water, but Titan has rivers, lakes, and seas, made not of water, but of liquid methane and ethane. The Cassini spacecraft, during its 13 years in orbit around Saturn, mapped Titan's hydrocarbon seas in the northern hemisphere and found them to be substantial. Ligeia Mare, the second largest, covers an area comparable to Earth's Lake Superior. The question that some astrobiologists have explored is whether life could exist in these methane seas using a chemistry based on methane as a solvent instead of water. The chemistry of such life would be radically different from any life on Earth. It would need to use different molecular backbones and different energy storage molecules because the standard biochemistry of terrestrial life depends on water. But there is no physical law that requires water as the solvent of life, only convention derived from the one example of life we know. Theoretical models have proposed candidate molecules that could form membranes stable in liquid methane, and if such membranes existed, they would have a characteristic effect on the acetylene and molecular hydrogen present in Titan's atmosphere, consuming them at predictable rates. Some measurements of Titan's atmosphere by Cassini showed depletion of hydrogen and acetylene near the surface consistent with this prediction. NASA's Dragonfly rotorcraft lander, scheduled to arrive at Titan in 2034, will explore the surface chemistry and search for prebiotic or potentially biotic molecules. Mars has occupied a central place in the human imagination as a possible abode of life for well over a century, and the scientific case for past habitability is now well established. Mars today is cold, dry, and thin atmosphered, with a surface bombarded by ultraviolet radiation and bathed in oxidizing chemicals that would be hostile to most terrestrial life. But Mars has not always been this way. Geological evidence from multiple Mars missions has established beyond reasonable doubt that liquid water flowed on Mars in its ancient past. River valleys, lake beds, delta deposits where rivers met standing bodies of water, and mineral compositions that form only in the presence of liquid water have been found across the Martian surface. Gale Crater, where NASA's Curiosity rover has been exploring since 2012, was once the site of a lake that persisted for millions of years, long enough, by Earth standards, for the emergence of microbial life. Ancient Mars appears to have had a denser atmosphere, a magnetic field that partially shielded the surface from solar wind, and surface temperatures that at least seasonally allowed liquid water. Precisely when and why Mars lost its warmth and its water is still being researched, but the habitability window may have lasted long enough for life to arise and potentially survive in subsurface refugia. Liquid water environments protected from the harsh surface conditions, possibly still existing today in deep brine aquifers. The Perseverance rover, which landed in Jezero crater in February 2021, is collecting rock samples from ancient lake sediments that will eventually be returned to Earth for detailed analysis. These samples represent the best opportunity we have had to search for chemical or structural biosignatures in ancient Martian geology. The history of Mars observation from Earth is itself a fascinating story of how human perception shapes what we see. Giovanni Schiaparelli, the Italian astronomer who mapped Mars in detail during the opposition of 1877, described features on the planet's surface as canali, the Italian word meaning channels or grooves. When this was translated into English as canals, it acquired a connotation of artificial construction that the original Italian did not necessarily imply, but the damage was done. Percival Lowell, an American astronomer of independent means, spent the last years of the 19th century and the first years of the 20th at an observatory he built in Flagstaff, Arizona, entirely devoted to studying Mars and documenting his increasingly elaborate theory that the canals were an irrigation network built by a dying civilization trying to distribute water from the polar ice caps to the drying equatorial regions. Lowell published 3 books on Mars and produced detailed maps of what he believed he saw. The scientific community was skeptical, but the public was captivated, and the image of Mars as the home of an ancient, perhaps extinct civilization embedded itself deeply in the cultural imagination. H.G. Wells wrote The War of the Worlds in 1898, Edgar Rice Burroughs began his Barsoom series in 1912, and the template for The Martian, intelligent, ancient, possibly desperate, was set for generations of science fiction. When spacecraft eventually revealed the actual Martian surface in the 1960s, the absence of any canals was not surprising to scientists, but the cultural template Lowell helped establish persists, still shaping how popular culture imagines the possibility of life next door. The Viking landers, which arrived on Mars in 1976, conducted the first direct biological experiments on another world and produced results that have been debated for nearly 50 years. Viking 1 and Viking 2 each carried a biology package containing 3 separate experiments designed to detect metabolic activity in Martian soil, a labeled release experiment that added radioactive carbon to moist soil and looked for gas production indicating microbial respiration, a gas exchange experiment that moistened soil and looked for changes in the atmosphere above it, and a pyrolytic release experiment that exposed soil to light and labeled carbon dioxide and looked for organic synthesis. The results of the labeled release experiment were striking. The Martian soil produced a burst of carbon dioxide consistent with biological activity, and the reaction was suppressed when the soil was heated enough to kill any microbes. This was exactly what the principal investigator, Gilbert Levin, had designed the experiment to detect, and he argued for the rest of his life that it represented positive evidence for life on Mars. The scientific consensus, however, attributed the results to highly reactive chemicals in the Martian soil, specifically iron peroxides or perchlorates, that could produce a similar oxidative reaction without any biology. The complication is that this interpretation predicts that the organic carbon in Martian soil should be destroyed, and indeed the other Viking experiments detected no organic molecules. Whether this absence of organics reflects the true destruction of all organic compounds by soil chemistry or the inadequacy of Viking's detection sensitivity remains debated. The question of what Viking actually found on Mars in 1976 is genuinely unresolved. Beyond the planets and moons of our solar system, the search for life has an older and in some ways more intimate dimension, the question of life in our cosmic neighborhood, nearby stars at distances of tens to hundreds of light years. In 2016, astronomers announced the discovery of Proxima b, a planet orbiting in the habitable zone of Proxima Centauri. the closest star to the Sun at a distance of only 4.24 light-years. Proxima Centauri is a red dwarf star, significantly cooler and smaller than the Sun, and Proxima b, if it is rocky and has retained an atmosphere, would orbit it at a distance of only 0.04 astronomical units, much closer than Mercury orbits the Sun, completing each orbit in about 11 days. Red dwarf stars present both opportunities and challenges for habitability. Their extreme longevity, they burn for trillions of years compared to the Sun's approximately 10 billion-year lifespan, means that any life around them would have extraordinarily long periods for evolution. But red dwarfs are also prone to powerful stellar flares that emit intense UV and X-ray radiation, which could strip the atmosphere from close-orbiting planets and sterilize their surfaces. Whether Proxima b has an atmosphere, whether it has been flare-sterilized, and whether it bears any resemblance to a habitable world is not yet known. But the fact that the nearest star to our own has a planet in its habitable zone has reinforced the view that habitable zone planets are extraordinarily common. The first detection of radio signals from another civilization, if it ever occurs, would be one of the most significant events in the history of our species. And the SETI community has thought carefully about what should happen next. The protocols developed by the SETI Institute and endorsed by various national and international bodies specify that the discoverer should verify the signal independently before making any announcement, should notify other observatories to attempt confirmation, should not respond to the signal without international consultation, and should report the discovery to the United Nations and the broader scientific community. These protocols are not legally binding, and it is unclear how well they would hold in practice given the speed of modern communication, but they represent a serious attempt to think through the social and political dimensions of first contact before it happens. The question of whether to respond to a detected signal is particularly complex. Some argue that any response would be dangerous, broadcasting our location and potentially inviting the attention of a civilization whose intentions and capabilities are unknown. Others point out that Earth has been broadcasting its presence through radio and television signals for nearly a century, and that any civilization capable of detecting our signals would already know we are here. The question of active messaging is therefore moot. The debate about whether to respond is part of a broader discussion about whether it is wise to send deliberate messages toward nearby stars at all. A practice called active SETI or METI, messaging extraterrestrial intelligence, that has generated significant controversy within the scientific community. The apparent contradiction between the expectation that the galaxy should be teeming with civilizations and the complete absence of any detected signal or visit is known as the Fermi paradox, after the physicist Enrico Fermi, who is said to have raised the question during a lunch conversation in 1950. The argument runs roughly as follows. The galaxy is approximately 10 billion years old, and many stars are billions of years older than the Sun. If intelligent life and technological civilization are reasonably common, some of them should have had billions of years head start on us. Even without faster-than-light travel, a civilization that spread at a small fraction of the speed of light could colonize the entire Milky Way in a few tens of millions of years, and well, a small fraction of the galaxy's age. The galaxy should be full of evidence for such civilizations. We see nothing. The Fermi paradox has generated dozens of proposed resolutions which fall broadly into a few categories. The first is that intelligent life is genuinely very rare, that the barriers to its development are so severe that only one or a handful of civilizations exist in the galaxy at any given time, and we happen to be one of them. This is often called the rare Earth hypothesis, or the Great Filter hypothesis. The second is that civilizations tend to destroy themselves through nuclear war, ecological collapse, or some other catastrophe before they have time to spread. The third is that civilizations exist but have not been heard because they communicate in ways we are not listening for, or because the distances involved mean signals have not reached us yet. The fourth is that civilizations exist and are aware of us but have chosen not to contact us, the zoo hypothesis. Each of these has implications that range from reassuring to deeply unsettling. The Great Filter concept, developed by the economist Robin Hanson in 1998, asks where in the progression from simple chemistry to galaxy-spanning civilization the catastrophic bottleneck lies. The good news scenario is that the filter is behind us, that the development of eukaryotic cells, or sexual reproduction, or multicellular life, or intelligence, or some other step, is extraordinarily difficult, and that we have already passed through this almost impossibly improbable transition. On this view, simple microbial life might be common across the universe, but complex animal life and intelligence are extraordinarily rare, perhaps even unique. Finding Mars completely sterile, no microbial life, no ancient biosignatures, would actually be somewhat reassuring under this framework, because it would suggest that even simple life is rare and that we have passed through the filter. The bad news scenario is that the filter is ahead of us, that it is not the development of life or intelligence that is rare, but the survival of technological civilizations through the period of their most dangerous capabilities. On this view, the absence of other civilizations reflects the fact that they all destroyed themselves before reaching the stage of interstellar colonization, and we are likely to do the same. Finding evidence of microbial life on Mars, even ancient biosignatures, would paradoxically make this darker interpretation more probable, because it would confirm that life arises readily and push the filter toward the later civilizational stages. The implications of astrobiology for the long-term future of our species are thus intimately intertwined. The question of what extraterrestrial life might actually look like, whether intelligent or not, has been transformed by decades of discoveries about the diversity of life on Earth. Astrobiology, the scientific discipline that studies the origin, evolution, and distribution of life in the universe, began by largely assuming that extraterrestrial life, if it existed, would be similar to terrestrial life in its basic chemistry, using carbon, water, and the basic metabolic pathways common to all Earth life. The discovery of extremophiles has dramatically broadened this picture. Extremophiles are organisms that thrive in conditions once thought to be incompatible with life. In the boiling water of hydrothermal vents, in highly acidic mine drainage, in the cold brines of Antarctic lakes, in highly alkaline soda lakes, in the deep rock of the Earth's crust kilometers from the surface, in the intense radiation of nuclear reactor cooling pools, in the vacuum of the outer atmosphere, and in the deep anoxic sediments of the ocean floor. Life on Earth is far more chemically versatile and environmentally tolerant than was once understood, and this has given astrobiologists greater confidence that life, if it arises on other worlds with different environmental conditions, might persist through extraordinary challenges. The deep subsurface biosphere, the community of microorganisms living in rock several kilometers below the surface, metabolizing at almost imperceptibly slow rates, independent of sunlight and surface chemistry, has been estimated to contain a substantial fraction of Earth's total biomass, suggesting that life's preferred habitat might be underground rather than at the surface, and that rocky planets broadly might support life regardless of their surface conditions. The chemistry of life itself, the specific molecules that terrestrial life uses, and whether these are universal or parochial, is a question of deep importance for the search for life elsewhere. All life on Earth uses the same fundamental chemistry: DNA for information storage, RNA as an intermediate, and proteins as functional molecules. The genetic code, the specific mapping between DNA sequences and amino acids, is essentially universal across all terrestrial life, suggesting that it was established very early in life's history and has been maintained since. Carbon is the backbone of all terrestrial biomolecules because of its extraordinary versatility. It forms 4 stable bonds and can produce chains of almost unlimited length and branches of almost unlimited complexity. Silicon, which sits directly below carbon in the periodic table, shares some of these properties and has been proposed as an alternative backbone for life in environments too hot for carbon compounds. But silicon chemistry is significantly less versatile than carbon chemistry in the temperature and chemical ranges accessible to water-based life, and there is no evidence from any source for silicon-based biological chemistry. Phosphorus plays a central role in terrestrial biochemistry. It is the backbone of DNA and RNA and the energy currency molecule ATP, and was briefly controversially claimed to be replaceable by arsenic in one terrestrial organism. The claim was retracted, but it generated a productive scientific conversation about how essential each specific element is to life's chemistry. The phenomenon of panspermia, the hypothesis that life can travel between worlds aboard rocks ejected from one planet by large impacts and eventually landing on another, has moved from speculation to a scientifically respectable idea over the last few decades. The mechanisms of lithopanspermia, as the rocky version is called, are well studied. Mars and Earth exchange approximately 10 kilograms of material per year in the form of meteorites ejected by large impacts. The transit time for a rock from Mars to Earth is typically a few million years, though faster transfers of tens of thousands of years are possible. Bacteria and other microorganisms can survive for millions of years in the protected interior of a rock if they are dormant. The radiation environment of interplanetary space would be damaging, but not necessarily lethal, to organisms deep within a meter-sized rock. Entry heating on arrival is a serious challenge, but rocks do not uniformly heat during atmospheric entry, and the interior of a large rock can remain cool even as the exterior ablates. Laboratory experiments have shown that bacterial spores can survive simulated impacts, space radiation, and atmospheric entry. Whether panspermia has actually occurred in our solar system is unknown, but it is considered physically plausible by mainstream astrobiologists. The implication is interesting. Life on Mars and life on Earth, if both exist, might have a common ancestor, shared via rock transfer early in solar system history, making any life we find in the solar system potentially our most distant relatives rather than truly alien life. The possibility of directed panspermia, the intentional seeding of life on other worlds by an intelligent civilization, was proposed seriously by Francis Crick, co-discoverer of the structure of DNA, and Leslie Orgel in a 1973 paper. Crick and Orgel argued that the universality of the genetic code and the specific selection of certain elements in terrestrial biochemistry, particularly the use of molybdenum, which is rare on Earth but common in cosmic chemistry, suggested that life on Earth might have been introduced by an intelligent source that chose its biochemistry deliberately. This idea has not found mainstream acceptance and is considered by most biologists to be an unnecessary hypothesis that explains no feature of terrestrial life better than natural abiogenesis. But Crick's willingness to take it seriously reflects the genuine mystery that surrounds the origin of life. The specific origin of life on Earth, how chemistry crossed the threshold into self-replicating, evolving biological systems, is one of the outstanding unsolved problems in science. In the absence of a complete natural explanation for that origin, directed seeding remains a logically possible alternative, even if it is not considered scientifically parsimonious. The modern era of government engagement with UAP, unidentified aerial phenomena, represents a striking shift in the official stance that has been maintained, at least publicly, since the closure of the U.S. Air Force's Project Blue Book in 1969. Project Blue Book, which ran from 1952 to 1969 and collected over 12,000 reports, was terminated with the conclusion that UAP represented no threat to national security and that there was no evidence of any phenomenon beyond the capability of current science to explain. For decades after 1969, official U.S. policy was effectively to dismiss UFO reports as not worthy of serious investigation. This changed markedly in the late 2010s. In December 2017, the New York Times published an article revealing the existence of the Advanced Aerospace Threat Identification Program, a secretive Pentagon program that had been quietly funded from 2007 to 2012 to investigate UAP. The article was accompanied by declassified footage from U.S. Navy FA-18 jets recording encounters with objects displaying flight characteristics that the pilots could not explain. These videos, which showed objects moving at high speed without visible propulsion, hovering, and appearing to react to the jet's presence, were subsequently confirmed as authentic by the Pentagon. The following years saw an acceleration of official engagement, congressional hearings, the establishment of a dedicated UAP investigation office, and the release of multiple official reports acknowledging that a significant number of UAP incidents involving military personnel could not be explained. In June 2021, the Office of the Director of National Intelligence released a 9-page unclassified report on 144 UAP incidents involving military personnel between 2004 and 2021, acknowledging that most remained unexplained. The Navy videos that were released along with the 2017 New York Times article became among the most widely viewed and discussed pieces of evidence in the modern UAP conversation. 3 videos, designated FLIR 1, Gimbal, and Go Fast, each showed infrared footage from targeting systems aboard FA-18 jets encountering objects that the pilots could not identify. The FLIR 1 video, taken during the 2004 USS Nimitz encounter off the coast of California, shows a white oval object that the pilots reported had descended from 80,000 feet to approximately 50 feet above the ocean in seconds before they arrived, was hovering with no visible means of propulsion, and then accelerated away at extreme speed as they attempted to intercept it. Commander David Fravor, the pilot of the lead jet during the encounter, subsequently gave multiple interviews and testimony describing what he observed as unlike any aircraft he had encountered in his extensive military career. The gimbal video from 2015 shows a rotating object. The apparent rotation is actually an artifact of the targeting pod's gimbal mechanism, hence the name, moving against the wind with no visible exhaust or propulsion. The audio of the pilot's commentary is widely quoted. When one pilot observes the object it's rotating, the other responds, "What the hell is that thing?" These videos are notable not because they prove extraordinary explanations, but because they are authenticated pieces of military footage showing objects with flight characteristics that the relevant personnel, trained military aviators using sophisticated sensor systems, were unable to explain, and that official investigation has not definitively explained. The question of what any of this official UAP data actually means is one that serious researchers approach with considerable caution. The range of explanations for UAP incidents is wide, and the explanations most likely to be correct are not the most dramatic ones. At one end of the spectrum, many UAP reports are explained by conventional causes: atmospheric phenomena, sensor artifacts, misidentified aircraft, drones, balloons, or natural bioluminescent phenomena. The acknowledged difficulty in explaining some military UAP incidents may reflect primarily the specific limitations of the sensor systems involved, the challenges of interpreting single-sensor data, the absence of independent corroboration, or classified capabilities of adversary nations that the investigating offices cannot publicly acknowledge. The intelligence community has consistently noted that foreign adversary hypersonic or autonomous systems are among the explanations being actively considered for the most unexplained cases. At the other end of the spectrum, the hypothesis that some UAP represent non-human technology, whether extraterrestrial from another dimension or of some other exotic origin, is the one that generates the most public interest, but is also the one that requires the most extraordinary evidence. The scientific standard of extraordinary claims requiring extraordinary evidence has not been met for any UAP incident on the public record. The responsible position is to hold the question open, take the phenomenon seriously, investigate rigorously, and withhold conclusions until the evidence warrants them. Astronomers have, in recent years, identified a small number of objects in the solar system whose origin and properties have generated speculation about possible artificial origin, while the scientific consensus has concluded natural explanations are more likely. The most prominent was Oumuamua, the first known interstellar object to pass through our solar system, detected in October 2017 by the Pan-STARRS survey telescope in Hawaii. Oumuamua exhibited several properties that were unusual for a natural object. Its shape appeared extremely elongated. Early estimates suggested a width-to-length ratio of approximately 1:10, far more extreme than any known solar system object. It was highly reflective, suggesting an unusual surface composition, and most puzzling, it accelerated away from the Sun faster than could be explained by solar gravity alone, a phenomenon called non-gravitational acceleration that is normally attributed to cometary outgassing, but for which no cometary activity was detected. Avi Loeb, the Harvard astrophysicist and chair of the university's astronomy department, proposed in 2018 that Oumuamua's properties were consistent with it being a thin artificial sail, essentially a piece of alien technology, and pursued this argument at book length in his 2021 book, Extraterrestrial. The mainstream astronomical community considered this interpretation far less likely than natural explanations involving a novel type of comet composed of hydrogen ice or a fragment of a Pluto-like body with unusual chemical composition. A second interstellar object, Borisov, detected in 2019, behaved much more like a conventional comet and generated no controversy. Oumuamua remains unexplained in all its details, though most astronomers are confident the explanation is natural. The discovery of phosphine in the atmosphere of Venus in 2020 was briefly one of the most exciting and contested moments in astrobiology. A team led by Jane Greaves at Cardiff University announced in September 2020 that they had detected phosphine, a molecule consisting of one phosphorus atom and 3 hydrogen atoms, in the clouds of Venus using data from the James Clerk Maxwell telescope and the ALMA array. Phosphine on Earth is produced almost exclusively by biological processes or by industrial chemistry. In the reducing atmospheres of the gas giants Jupiter and Saturn, it can be produced abiotically, but in Venus's highly oxidizing atmosphere, no known abiotic chemistry can produce phosphine in quantities remotely close to what the team reported. The announcement was met with intense scientific interest and significant skepticism. Multiple teams immediately began reanalyzing the data. Over the following months, issues with the data processing were identified that substantially reduced the estimated amount of phosphine, and the statistical significance of the detection was downgraded. The consensus as of 2024 is that the evidence for phosphine in Venus's atmosphere is at best marginal, and the claim has not been independently confirmed. But the episode was instructive. It showed the scientific community actively engaged with and critically evaluating a potential biosignature claim, and it reinvigorated interest in Venus's cloud layers, which at altitudes of 48 to 60 kilometers have temperatures and pressures similar to Earth's lower atmosphere, and had been proposed as a potential habitat for microbial life as early as the 1960s. Among the many fascinating dimensions of the UFO and alien contact topic is the cultural history of how different human societies have imagined and represented visitors from the sky. The modern flying saucer era, with its specific imagery of disc-shaped craft, grey humanoid occupants, and contact narratives involving medical examinations and messages of cosmic importance, is largely a product of the post-1947 period in Western, predominantly American culture. Kenneth Arnold's 1947 report of 9 unusual objects over Mount Rainier, misquoted into the phrase flying saucers, was the spark. The Roswell incident of the same year, initially reported as a recovered flying disc and subsequently retracted by the military, was the accelerant. Within a year, the specific visual vocabulary of the flying saucer was established in the cultural imagination, reinforced by science fiction magazines and films that drew on the public fascination. The grey alien, the now iconic image of a being with a large hairless head, oversized black eyes and a small body, emerged in American popular culture in the 1960s and became dominant after the 1987 publication of Whitley Strieber's Communion, with its memorable cover illustration. Anthropologists and cultural historians note that this specific imagery is not universal. Reports from South America, Africa, and Asia in the same period often describe very different kinds of entities, suggesting that the specific imagery is culturally mediated rather than universally perceived. This does not settle the question of whether any genuine encounters underlie the reports, but it complicates the use of visual similarity in witness accounts as evidence for a common external source. The history of official government responses to UFO reports is itself a fascinating and often convoluted story of institutional incentives, public relations management, and genuine uncertainty. In the United States, the 1947 surge of UFO reports prompted the creation of Project Sign, later renamed Project Grudge, and then Project Blue Book, 3 successive programs that in various ways investigated, catalogued, and attempted to explain UFO sightings. The Condon Report, a scientific study commissioned by the Air Force and conducted by a team at the University of Colorado under physicist Edward Condon, concluded in 1968 that further scientific study of UFOs could not be justified. The report was criticized both for its negative framing from the start. Documents emerged suggesting that Condon had concluded the study would find nothing before it began, and for its methodology, which some argued was designed to debunk rather than investigate. Its conclusion provided the basis for closing Project Blue Book in 1969. In the Soviet Union, a parallel and secretive investigation program existed, collecting military and civilian reports with an emphasis on potential threats rather than scientific inquiry. After the Soviet Union's dissolution, some of this material became available to researchers and revealed cases strikingly similar in character to Western reports, suggesting that whatever the phenomenon is, it is not specific to any cultural or political context. The French government's GEPAN program, established in 1977 under the space agency CNS, took a scientific approach to UAP that was unusual for its time and remains admirable. GEPAN, later renamed SEPRA and then GEPAN, collected reports, conducted field investigations, applied rigorous scientific analysis, and published findings including the cases it could not explain. The Valensole case, in which a farmer named Maurice Mass reported a close encounter with two small beings examining his crops in 1965, was investigated in detail by GEPAN and found to involve physical ground traces, a hole in the earth consistent with the central support Mass described, and soil at the site that showed altered characteristics compared to surrounding soil, including reduced moisture content. The Trans-en-Provence case in 1981, in which a farmer reported a disc-shaped object landing in his garden, was also investigated by GEPAN and produced a detailed report noting unusual changes in the vegetation at the landing site, including biological and biochemical alterations in plant samples that GEPAN could not attribute to any known cause. These French investigations represent the most scientifically rigorous analysis of physical evidence from UAP encounters that has been conducted by any government body and published in full. Their conclusions are characteristically cautious. They do not claim the encounters were extraterrestrial, but they document genuine anomalies that were not explained by conventional causes. The broader question of how we should interpret the witness testimonies of thousands of people who report close encounters, unusual craft, or contact experiences is one of the most challenging in this entire field. Psychologists have studied these reports extensively. Some patterns are clear. Sleep paralysis, a hypnagogic or hypnopompic state between sleep and waking in which the body is paralyzed and hallucinations are common, can explain a subset of encounter reports, particularly those involving beings entering bedrooms. The emotional and memory distortions that accompany traumatic or highly unusual experiences can explain inconsistencies in witness accounts over time. Hypnosis, widely used in the 1980s and 1990s to recover memories of alleged abduction experiences, is now well established to be highly unreliable and capable of generating detailed false memories, which means that many hypnotically recovered encounter narratives cannot be taken as accurate records, but a significant subset of encounter reports come from individuals who are not under hypnosis, who have corroborating witnesses, who are not asleep, and who resist simple psychological explanations. The consistency of certain details across independent reports from people with no known contact with each other, specific details about the appearance and behavior of reported entities, the physical effects of close proximity to unusual craft, the specific emotional states produced, is difficult to account for purely through cultural contamination or common psychological processes. This does not mean the reports are accurate accounts of physical events, but dismissing them entirely as delusion or deception requires ignoring a substantial body of unusual data. The scientific search for life as it exists outside the specific context of Earth, not just life similar to terrestrial life, but life as a general phenomenon, has produced the concept of the tree of life and the recognition that all known life on Earth belongs to a single tree with a common ancestor. If life had originated independently on Earth more than once, we would expect to find organisms using genetic codes different from the universal code, or using different amino acids or different base pairs in their DNA. We do not. All life on Earth, from bacteria to blue whales, uses the same genetic code, the same 20 amino acids, the same DNA base pairs. This biochemical unity is powerful evidence that all Earth life descends from a single ancestral population, Luca, the last universal common ancestor. It is not evidence that life could only have arisen once, but it is consistent with the possibility that the specific conditions that produced life on early Earth did so only once, and that all subsequent life is descendant from that single origin. If a shadow biosphere, a second independent origin of life, exists on Earth today using different biochemistry, we would have great difficulty detecting it with tools calibrated to the biochemistry we already know about. Searches for shadow biosphere organisms have so far found nothing, but the search has not been exhaustive and may never be. The chemistry of the interstellar medium, the gas and dust between stars, has been a source of continuous and deepening fascination for astrobiologists. Radio astronomy has identified more than 200 distinct molecular species in interstellar space, including many of the building blocks of biology. Glycine, the simplest amino acid, has been tentatively detected in interstellar clouds and confirmed in samples returned from Comet Wild 2 by the Stardust mission in 2006. The Murchison meteorite, which fell in Australia in 1969 and has been more thoroughly studied than almost any other extraterrestrial sample, contains more than 70 different amino acids, only 19 of which are found in terrestrial biology, along with nuclear bases, sugars, and a range of other organic molecules. The presence of complex organic chemistry in meteorites and comets implies that the building blocks of life are produced ubiquitously in space through abiotic chemistry and are then delivered to planetary surfaces by the continuous rain of rocky and icy material from space. This has led to the concept of the cosmic chemistry of life, the idea that the molecules of life are not specifically biological products but are the natural output of the organic chemistry that proceeds throughout the universe. If the ingredients of life are universal, the barrier to life's origin may lie not in the availability of raw materials but in the specific process by which those materials assembled into self-replicating systems. Understanding this process remains one of the deepest unresolved problems in science. The James Webb Space Telescope, which began scientific operations in 2022, has transformed several areas of observational astronomy and has the potential to make the first genuinely significant contributions to the search for biosignatures in exoplanet atmospheres. JWST's primary advantage over its predecessors is its infrared sensitivity and its large collecting area, which allow it to analyze the atmospheres of exoplanets in transit as they pass in front of their stars, by detecting the specific wavelengths of light absorbed by molecules in the planetary atmosphere. Different molecules absorb different wavelengths, and the pattern of absorption features in the transmission spectrum of a planet's atmosphere is effectively a molecular fingerprint that identifies what the atmosphere contains. JWST can detect water vapor, carbon dioxide, methane, and potentially oxygen and ozone in the atmospheres of sufficiently nearby exoplanets. In 2023, JWST reported tentative evidence of sulfur dioxide in the atmosphere of the hot Jupiter WASP-39b, confirming that atmospheric chemistry could be detected even for this challenging target. The TRAPPIST-1 planets, which are more interesting from a habitability perspective, are being observed with multiple JWST programs. The first results for TRAPPIST-1b found no evidence of a thick carbon dioxide atmosphere, suggesting it may be an airless rock. Results for the more promising inner habitable zone planet, TRAPPIST-1c, are expected. These observations are the beginning of a multi-decade program that will eventually characterize the atmospheres of dozens of rocky exoplanets. The probability that one of them will show an atmospheric chemistry inconsistent with abiotic processes increases with each observation. The concept of the cosmic perspective, the view of Earth and humanity from a vast astronomical distance, has been powerfully shaped by a small number of images and observations that have cultural as well as scientific significance. The blue marble photograph taken by the Apollo 17 astronauts in December 1972 and showing the whole Earth as a suspended sphere in the darkness of space became one of the most widely reproduced photographs in history and is widely credited with stimulating the environmental movement by making visible the fragility and unity of the biosphere. The Voyager 1 spacecraft, at the suggestion of Carl Sagan, turned its camera back toward the inner solar system in February 1990 from a distance of approximately 6 billion kilometers and photographed the Earth as a tiny speck in a sunbeam. the pale blue dot image. Sagan's meditation on the image, in which he described the Earth as a mote of dust suspended in a sunbeam and noted that every human being who ever lived had spent their entire lives on this small stage, remains one of the most widely quoted passages in popular science writing. These images do something that neither pure science nor pure philosophy can do individually. They provide visceral, experiential context for the abstract understanding that the universe is vast and our place in it is small. Whether there is other life in the universe or not, this perspective, the recognition that we are one small world among an enormous number of worlds, seems to many people to be among the most important shifts in human self-understanding that the scientific enterprise has produced. The possibility that intelligent life elsewhere in the universe might be so different from us as to be unrecognizable has been seriously explored in astrobiology and in philosophy of science. The assumption underlying most SETI work is that technological intelligence will produce radio or optical signals that we can detect and recognize as artificial. This assumes a certain convergence of technological development and a certain overlap in the physics of communication. But there is no reason in principle why this should be the case. An intelligence that evolved in a radically different sensory modality, in the deep ocean, in a gas giant's atmosphere, in the rock of a planetary crust, might develop completely different technologies that leave no radio frequency signature at all. More speculatively, an intelligence that evolved over billions of years might have developed beyond the phase of radio communication long ago and might now operate in ways that our current physics cannot even describe. The zoo hypothesis, that advanced civilizations are aware of us but have chosen not to interfere, is often treated with skepticism because of the difficulty of maintaining a universal non-contact policy across all members of a civilization for the necessary timescales. But the broader point, that the absence of detected signals might say more about the limitations of our search strategies than about the absence of other intelligence, is taken seriously by researchers. The science fiction concept of transcendence, of civilizations evolving beyond physical substrates and into forms of pure information or energy, is genuinely reflected in some serious discussions about the endpoint of civilizational development. The archaeological and anthropological record of human encounter with the sky is a rich and often misunderstood subject. Ancient astronaut theories, the claim, popularized in Erich von Däniken's 1968 book Chariots of the Gods, that advanced extraterrestrial beings visited Earth in the prehistoric past and were responsible for various ancient architectural achievements, have been comprehensively rejected by mainstream archaeology and anthropology. The specific claims that the pyramids, the Nazca Lines, the megalithic monuments of the ancient world could not have been built without alien assistance rest on a systematic underestimation of ancient human ingenuity and on a selective reading of the evidence. The actual archaeological record shows extensive evidence of the tools used to quarry and move megalithic stones, the gradual development of construction techniques through trial and error, and the indigenous cultural context within which these monuments were built. Attributing them to alien assistance is not only scientifically unsupported, but has sometimes been criticized for implying that ancient non-European peoples were incapable of such achievements without external intervention, a suggestion that many historians and anthropologists find offensive as well as wrong. This does not mean that nothing unusual or unexplained exists in the ancient record. It means that the explanations for ancient achievements are found in the extraordinary capabilities of ancient humans, not in extraterrestrial visitors. The deep history of the sky in human culture, the mythologies, the cosmologies, the religious systems centered on celestial bodies and celestial events, tells us something important about the relationship between human consciousness and the universe above us. Every known human culture has looked at the sky and found meaning there, the movements of the sun and moon tracked for agricultural and navigational purposes, the stars arranged into constellations and populated with mythological figures, the planets recognized as distinctive wanderers and associated with divine powers, meteorological and astronomical events interpreted as omens of earthly significance. This universal attention to the sky reflects partly its practical importance. For navigation, for timekeeping, for agriculture, and partly something deeper. The sky is where the things that are most powerful and most beyond human control are found. The sun that makes crops grow, the rain that waters them, the storms that destroy them, all come from above. The sky is where gods live in most of the world's religious traditions, not because people were misled, but because the sky genuinely is where the forces most important to human survival originate. The question of whether anything is actually up there looking back is not new. It is perhaps the oldest question in human intellectual history, and the fact that we now have the means to begin answering it scientifically represents one of the great pivots in that history. The Kepler Space Telescope, launched in 2009 and retired in 2018, fundamentally changed our understanding of how many planets exist in the universe. Its method was elegant in concept, though extraordinarily demanding in execution. It stared continuously at a single field of approximately 150,000 stars in the constellation Cygnus, measuring their brightness with extreme precision, and waited for the tiny dip in starlight that occurs when a planet passes in front of its star, a transit. The fractional decrease in brightness caused by an Earth-sized planet transiting a Sun-like star is approximately 0.008%, a change so small it is completely invisible to the naked eye and requires extraordinarily stable photometric measurements to detect reliably. Kepler detected this signal for thousands of planetary systems, transforming the field of exoplanet science from a speciality with a handful of known worlds to a discipline cataloguing thousands. The statistical implications of Kepler's discoveries were staggering. By extrapolating from the fraction of stars that showed transits and accounting for the geometric probability that any given planetary system would be oriented with its orbital plane pointing toward Kepler's view, astronomers could estimate the total frequency of planets around stars. The conclusion was that planets are extraordinarily common. Virtually every star has at least one, and many have several. The concept of our solar system as representative of what star systems look like has been thoroughly dismantled. The diversity of planetary architectures is vast, and the specific structure of our solar system, Jupiter in its current orbit, Earth in its habitable position, the outer solar system of ice giants, turns out to be one of many configurations, not necessarily a typical one. The discovery of biosignatures, chemical or physical evidence that life is or was present in materials from space, has a longer history than many people realize. The Murchison meteorite, which fell in rural Victoria, Australia, in September 1969, was an extraordinary scientific gift. It fell in a sparsely populated area, was recovered quickly before significant contamination could occur, and turned out to be a carbonaceous chondrite, a type of primitive meteorite that preserves the chemistry of the early solar system. Detailed analysis over the subsequent decades revealed it to contain a remarkable inventory of organic molecules, more than 70 amino acids, including many not found in terrestrial biology. Purines and pyrimidines, the nitrogen-containing bases that form the information-carrying components of DNA and RNA. Sugars, including ribose, the backbone of RNA, and a variety of other complex organic compounds. The amino acids in Murchison show isotopic compositions consistent with formation in space rather than terrestrial contamination, and the specific distribution of molecular varieties differs from what terrestrial biology produces. The presence of these molecules in a meteorite from the early solar system confirms that the chemistry of life is not unique to Earth. It is produced by abiotic processes in space and delivered to planetary surfaces throughout the history of the solar system. Whether these delivered molecules contributed to the origin of life on Earth, or whether Earth's life developed its biochemistry entirely independently, is unknown. But the raw materials were available on the early Earth from extraterrestrial delivery, as well as from terrestrial chemistry. The atmosphere of a planet tells us an enormous amount about what is happening on and inside it, and for inhabited planets it preserves the signatures of life in ways that could be detectable from vast distances. Earth's atmosphere is profoundly different from what it would be in the absence of life. Before life arose, Earth's atmosphere contained primarily nitrogen, carbon dioxide, and water vapor, similar to the current atmospheres of Mars and Venus, which have no biosphere. Life changed this. photosynthesizing organisms, first cyanobacteria, beginning approximately 2.7 billion years ago, and then, in their evolved form, all green plants and algae, began producing oxygen as a byproduct of using sunlight to convert carbon dioxide and water into organic matter. Oxygen accumulated in the atmosphere gradually, triggering the Great Oxidation Event approximately 2.4 billion years ago, transforming Earth's chemistry and the possibilities for life. Today, Earth's atmosphere contains approximately 21% oxygen, an amount wildly out of chemical equilibrium with the surface rocks, which would absorb all the atmospheric oxygen within a few million years if biology stopped replenishing it. This chemical disequilibrium is the key biosignature, oxygen and methane coexisting in the same atmosphere, when they react with each other at rates that would deplete both in the absence of biological replenishment, is a powerful indicator of biology. An astronomer observing Earth from another star system with a sufficiently sensitive spectrograph could detect this disequilibrium and identify Earth as a world where something unusual, something consistent with life, is happening to its atmospheric chemistry. The question of how life on Earth actually began, the field of origin of life research, has seen significant progress in the last 2 decades, though a complete mechanistic account of the transition from chemistry to biology remains elusive. The RNA world hypothesis, first proposed in the 1980s, suggests that the earliest life used RNA as both the information-carrying and catalytic molecule, and that DNA took over as the information storage medium and proteins as the catalytic specialists later, once the RNA world was established. The hypothesis has substantial support. RNA can fold into complex 3-dimensional structures that catalyze specific chemical reactions, just as proteins do, and RNA is still central to information transfer and protein synthesis in all living cells. The ribosome, the cellular machine that synthesizes all proteins, is essentially a large RNA molecule with proteins attached for stability, and it may be a fossil of the RNA world preserved in all modern cells. The challenge is explaining how RNA itself arose. RNA nucleotides are complex molecules, and assembling them spontaneously under conditions plausible for the early Earth has proven extremely difficult chemistry. Recent work by researchers, including John Sutherland at the MRC Laboratory of Molecular Biology in Cambridge, has shown plausible prebiotic routes to the synthesis of RNA nucleotide precursors under conditions consistent with an early Earth mixing zone between volcanic inputs and dilute water. The chemistry is complex and contentious, but progress is real. Understanding how life began is not just of historical interest. It is the key to understanding whether life's origin was a near inevitable outcome of chemistry or an extraordinarily improbable accident, and therefore the key to estimating how common life might be across the universe. Exoplanet atmospheres have now been studied in enough detail to reveal not just their chemical composition, but something of their weather and circulation patterns. Hot Jupiters, gas giant planets orbiting extremely close to their stars, completing their orbits in days, are tidally locked, with one hemisphere perpetually facing the star and one perpetually facing away. The temperature difference between these hemispheres can be thousands of degrees Celsius, and strong winds must be driving enormous amounts of heat from the day side to the night side. Observations with the Spitzer Space Telescope and JWST have directly measured the temperature maps of hot Jupiter atmospheres, confirming the expected asymmetry and revealing the specific circulation patterns. Some hot Jupiters show offset hotspots. The point of maximum temperature on the day side is shifted from the substellar point by strong super-rotating equatorial jets. These atmospheric dynamics are studied not primarily because hot Jupiters are interesting places for life, they are not, but because understanding how planetary atmospheres behave under extreme conditions refines the models that will eventually be applied to the more interesting, more habitable worlds that JWST and its successors will characterize. Every hot Jupiter atmosphere studied is a calibration point for the models that will one day be used to interpret the spectrum of a pale blue dot orbiting a nearby star. The concept of the habitable zone has itself become more nuanced as planetary science has matured. The traditional habitable zone, sometimes called the Goldilocks zone, is defined as the range of distances from a star at which liquid water could exist on the surface of a rocky planet with a carbon dioxide atmosphere and appropriate albedo. This definition is useful but limited. It excludes the possibility of habitable environments inside the habitable zone. A planet too close to its star might be habitable if it has appropriate cloud coverage and atmospheric chemistry. It excludes the possibility of habitable environments outside the habitable zone. As we have seen with Europa and Enceladus, tidal heating can maintain liquid water far from any star's warmth. It assumes a specific atmospheric composition and does not account for the diversity of atmospheres that planets might have. And it applies primarily to surface habitability, ignoring the possibility of subsurface oceans on worlds that receive no stellar heating at all. Free-floating rogue planets, ejected from their original systems, could potentially maintain liquid water in deep subsurface environments warmed by radioactive decay and residual heat from formation for billions of years. The traditional habitable zone is a reasonable starting framework for identifying priority targets, but the space of potentially habitable environments in the universe is likely much larger than it implies. Life, as the extremophiles of Earth have taught us, is extraordinarily resourceful at finding energy wherever it exists and inhabiting environments that intuition would rule out. The astrobiological significance of the timing of life's appearance on Earth is worth dwelling on. Earth formed approximately 4.5 billion years ago. The evidence for liquid water on the early Earth begins almost immediately in the geological record. Zircon crystals dated to approximately 4.4 billion years ago show isotopic signatures consistent with formation in the presence of liquid water. The oldest direct evidence for life, carbon isotope signatures in ancient sedimentary rocks from Greenland, dates to approximately 3.8 billion years ago, and microbial body fossils have been found in Australian rocks approximately 3.5 billion years old. Life appeared on Earth within a few 100 million years of the planet becoming habitable, an extraordinarily rapid colonization by any geological standard. This rapidity has been interpreted in two opposite ways. Optimists argue that the speed of life's appearance suggests that the transition from chemistry to biology is actually not extremely difficult. Given the right conditions, it happens quickly. If this interpretation is correct, life might be common wherever habitable conditions exist for sufficient time. Pessimists argue that the speed is a selection effect. We can only observe life appearing early because if it had appeared late, we would not be here to observe it, since complex life requires enormous geological time to develop, and that the early appearance tells us nothing about the difficulty of the transition. This debate about what can be inferred from a sample size of 1 is genuine and has not been resolved. The concept of panspermia extends in its most extreme form to lithopanspermia between star systems. The possibility that life could travel on rocks ejected by large impacts from one stellar system and captured by another. The timescales involved are enormous. Interstellar distances mean that a rock traveling at a few kilometers per second would take millions or billions of years to travel between nearby stars. The survival of organisms over such timescales against radiation, temperature extremes, and cosmic ray bombardment seems extraordinarily challenging, but calculations suggest that a significant fraction of material ejected from a solar system at sufficient velocity to escape the star's gravity would be captured by other systems over cosmological timescales, and that if organisms in the interior of a rock could survive millions of years of interstellar transit, which is not obviously impossible for the most radiation-resistant microorganisms, then interstellar panspermia could have distributed life across the galaxy. The implications would be profound. If panspermia is effective over interstellar scales, the tree of life might not be a single planet tree but a galaxy-spanning network, and the life we find on other worlds might share a common ancestor with Earth life. Testing this idea is extraordinarily difficult. It would require finding life elsewhere, sequencing its biochemistry, and comparing it with Earth life at a level of chemical detail that reveals whether the two share common ancestry. The comparison would need to distinguish between common ancestry through panspermia and convergent evolution, two separate origins that arrived independently at similar biochemical solutions. This is a hard problem, but not an impossible one. The search for techno-signatures, signs of intelligence rather than mere biology, has diversified significantly from its original focus on radio communication. The logic behind looking for techno-signatures is that a technological civilization leaves marks on its environment that are detectable from vast distances and that could not plausibly be produced by natural processes. Radio emission was the first obvious techno-signature, but the range of possibilities extends much further. Laser pulses, narrow-beam optical signals, are actually more efficient than radio for long-distance communication in many situations, and SETI programs now systematically search for optical and near-infrared laser pulses from nearby stars. Artificial illumination on a planet's night side would be detectable in transit observations, since the night side of an inhabited planet would show excess light from artificial sources that would be absent on an uninhabited world. Industrial pollution of a planetary atmosphere, specifically chlorofluorocarbons, which are produced by industrial chemistry and have no known natural source, would be detectable in a sufficiently sensitive atmospheric spectrum and would be unambiguous evidence of industrial activity. The detection of chlorofluorocarbons in an exoplanet atmosphere would not necessarily imply a friendly or accessible civilization. It would simply indicate that chemistry is occurring there that requires intelligent intervention. But it would be an extraordinary discovery. Current telescope capabilities are probably insufficient to detect these signatures even in the atmospheres of nearby exoplanets, but the next generation of extremely large telescopes will approach the necessary sensitivity. The history of how humans have thought about the possibility of other inhabited worlds is a history of alternating expansion and contraction of what seemed possible. In ancient Greek philosophy, the atomist school, Leucippus, Democritus, Epicurus, argued for an infinite universe containing infinite worlds, some of which would be inhabited. The Stoic school argued for a single, finite universe with Earth at its center, and this view became embedded in Christian theology through Aristotle. For more than 1,000 years, the idea of other inhabited worlds was philosophically dangerous. It challenged the uniqueness of the incarnation and the special status of humanity in the divine scheme. Giordano Bruno, the 16th-century Italian philosopher and former Dominican friar, was burned at the stake in Rome in 1600, in part because he taught that the universe was infinite and contained an infinite number of inhabited worlds. Bruno was not primarily a scientist. His cosmological arguments were partly mystical, but his execution represents one of the most dramatic moments in the conflict between the ancient doctrine of Earth's uniqueness and the emerging understanding of the cosmos that the scientific revolution was producing. By the 17th century, with Copernicus, Galileo and Kepler having established the heliocentric system and the planetary nature of Earth, the question of other inhabited worlds was openly discussed by natural philosophers. Christian Huygens, the Dutch astronomer who discovered Titan in 1655, wrote extensively about the probability of life on other planets, and concluded that the planets of our solar system likely harbored inhabitants. The modern scientific approach to this question is continuous with this long history of gradual intellectual liberation from the assumption of terrestrial uniqueness. The specific claim of extraterrestrial visitation, that non-human intelligences have physically arrived at Earth in the present or recent historical past, is one that the scientific community has not accepted, not because it is considered logically impossible, but because the evidence for it has not met the standard required to overturn the null hypothesis that all observed phenomena have conventional explanations. This is a genuinely important distinction. Scientists are not claiming that Earth has never been visited. They are claiming that the evidence for visitation is insufficient to conclude that it has occurred. The standards of evidence in science are high for good reason. Human perception is unreliable, memory is reconstructive and easily distorted, witness testimony is highly susceptible to suggestion and contamination, and the psychological pull of extraordinary explanations can cause people to overweight unusual but explicable observations. The history of science contains many examples of phenomena initially attributed to extraordinary causes, telekinesis, levitation, healing miracles, clairvoyance, that proved on careful investigation to have mundane explanations. It also contains examples of phenomena initially dismissed as impossible: continental drift, ball lightning, meteorites, that turned out to be real. The appropriate response to unusual observations is careful investigation rather than either credulous acceptance or dismissive rejection. This is the approach that serious researchers in this area try to take, and it is the approach that has the best track record of eventually arriving at correct answers. The cultural phenomenon of alien contact narratives, the vast literature of abduction reports, encounter testimonies, channeled messages from extraterrestrial intelligences, and claims of ongoing covert contact, deserves respectful attention even if its literal claims are not scientifically validated. These narratives serve important psychological and cultural functions. Contact with an intelligence more powerful and knowledgeable than ourselves, offering guidance and perspective on humanity's place in the cosmos, is a motif that appears across human spiritual and religious traditions in many forms. The extraterrestrial contact narrative is, in many respects, the contemporary form of an ancient need. The need to feel that we are not alone, that there is something beyond the purely material world we inhabit, and that our struggles and confusions might be comprehensible to a wider intelligence that has seen similar things before. Whether or not any specific contact claim is literally true, the emotional and spiritual reality of the experience for those who report it is not in doubt, and the experiences often have profound and lasting effects on those who have them. The philosopher and cognitive scientist Michael Shermer has argued that the alien abduction narrative maps onto the structure of the shamanic journey: descent into another realm, encounter with non-human beings, acquisition of knowledge, return, in ways suggesting it draws on deep cognitive and neurological templates. This structural similarity does not tell us whether the experiences are generated externally or internally, but it places them in a broader context of human experience that deserves thoughtful engagement. The radio telescope has been one of the most important scientific instruments of the 20th and 21st centuries, and not only for SETI. Radio astronomy, which began in earnest in the 1930s when Carl Jansky at Bell Telephone Laboratories detected radio emission from the center of the Milky Way, has transformed our understanding of the universe by revealing phenomena invisible to optical telescopes. Pulsars, rapidly rotating neutron stars emitting beams of radio waves, were discovered by radio telescope in 1967. The cosmic microwave background radiation, the afterglow of the Big Bang, was detected by radio receivers in 1965. Quasars, the extraordinarily luminous cores of distant galaxies powered by supermassive black holes accreting matter at prodigious rates, were identified as radio sources before they were understood optically. The structure of our own galaxy has been mapped largely through radio observations of hydrogen, which emits radiation at a characteristic frequency. Molecules in interstellar space, including the organic molecules relevant to astrobiology, are identified through their radiospectral lines. The same telescopes that search for signals from extraterrestrial civilizations are the tools of mainstream astrophysics, which means that SETI observations can often be conducted parasitically alongside other science, observing the same stars and the same sky for different purposes simultaneously. The infrastructure of radio astronomy is both the best tool we currently have for detecting extraterrestrial signals and one of the most productive scientific instruments humanity has built for understanding the physical universe. The possibility that artificial intelligence might be more detectable than biological intelligence, or might outlast it, has become an increasingly important thread in SETI thinking. If a technological civilization develops artificial general intelligence and subsequently artificial superintelligence, the resulting AI systems might be far more durable than their biological creators. A self-replicating AI system with access to sufficient energy could in principle operate on timescales of billions of years, vastly longer than the typical lifetime of a biological species. It would also likely be far more capable than its creators of dispersing throughout the galaxy, exploring and potentially colonizing new environments. If this is a typical trajectory of technological civilizations, then the universe might be populated not by biological intelligences, but by their AI successors. And the signatures we should be looking for might be those of artificial rather than biological intelligence. The specific physical signatures of an advanced AI civilization engaged in galactic-scale computation might be quite different from the radio beacons of a biological civilization trying to communicate. They might look more like unusual energy conversion patterns, anomalous waste heat signatures, or strange computational processes detectable through their effect on nearby matter. This thread of thinking is speculative, but it is taken seriously in the SETI community precisely because the development of AI is now a plausible near-term technological trajectory rather than a science fiction premise. The specific case of the 2004 USS Nimitz UAP encounters, which produced the FLIR 1 video and the testimony of Commander David Fravor and other Navy pilots, has received more rigorous journalistic and institutional scrutiny than almost any other UAP incident. The timeline of the encounter is well documented through multiple sources. The USS Princeton, the cruiser accompanying the Nimitz carrier strike group, had been tracking unusual targets on its radar for approximately 2 weeks before the incident, targets descending from above 80,000 feet to hover at approximately 50 feet above the ocean in a matter of seconds, then disappearing from radar. On November 14, 2004, Commander Fravor and his wingman were tasked to investigate an active radar contact. They found a white oblong object approximately 40 feet long hovering above a churning disturbance in the ocean's surface. When Fravor descended to intercept, the object appeared to react to his approach, ascending to meet him, and when he turned to intercept it, it accelerated away to the south at extreme speed. Fravor described the object as having no visible means of propulsion, no exhaust, no wings, and no surfaces consistent with conventional fixed-wing or rotary aircraft. The object was simultaneously picked up on the radar of a second pair of FA-18s that had been vectored to the area, and their FLIR targeting pod recorded it before it accelerated away. The incident is interesting not because it proves any extraordinary explanation, but because it illustrates the quality of some UAP encounters. Multiple trained military observers, instrumented aircraft, ship-based radar, and a subsequent official acknowledgement that the footage is genuine and the object unidentified. The scientific case for taking UAP seriously as an area of study, distinct from any specific claim about what UAP are, rests primarily on the argument that unexplained anomalies in our sensors and observations are always worth investigating rigorously. Science advances precisely by paying attention to things that do not fit existing models, and a pattern of anomalous observations reported by trained observers using sophisticated instruments in a consistent range of locations warrants investigation rather than dismissal. The Harvard professor Avi Loeb, through his Galileo project, has established a network of automated telescopes and sensors specifically designed to monitor the sky continuously for anomalous objects and to characterize them with multiple independent sensors simultaneously: optical cameras, infrared cameras, radar, and audio recorders. The goal is to accumulate high-quality data on UAP rather than relying on ad hoc sightings and imperfect single-sensor recordings. Whether this project finds anything extraordinary is unknown, but the methodology is scientifically sound. Design an instrument to observe the phenomenon of interest under controlled conditions with multiple independent sensors and analyze the resulting data without preconceptions. This is how science works, and there is no reason in principle why it should not be applied to UAP as to any other natural phenomenon. The reluctance of mainstream science to engage with UAP has been partly a response to the low quality of much of the available data and the association of the topic with fringe beliefs, but the gradual improvement in data quality, particularly from the military sensor systems, is beginning to change this. The atmosphere of Earth at very high altitudes, above the stratosphere, in the mesosphere and thermosphere, contains phenomena that were themselves once mysterious and are still not completely understood. Sprites, blue jets, and elves, collectively known as transient luminous events. Sprites are large-scale electrical discharges extending upward from thunderstorm tops to altitudes of 50 to 90 kilometers, appearing as reddish columns or clusters of lights lasting only milliseconds. Blue jets are narrower, blue-colored discharges that shoot upward from thundercloud tops to altitudes of approximately 40 kilometers. Elves are disc-shaped regions of faint luminescence, approximately 400 kilometers across, that appear at the very top of the ionosphere, in response to thunderstorm electromagnetic pulses. These phenomena were first photographed from aircraft in 1989, and in the decades since have been photographed from the International Space Station, from high-altitude research aircraft, and by ground observers with sensitive cameras. They occur in the same parts of the sky where UAP have been reported, particularly the sprites, which can be visible from the ground under the right conditions. Some researchers have proposed that early photographs and sightings of sprites and blue jets may have contributed to UAP reports. What is interesting from a broader perspective is that these transient luminous events, real, physical phenomena in Earth's upper atmosphere, were unknown to science until the 1980s and are still not fully explained. They are a reminder that the atmosphere of our own planet contains phenomena we did not know about until recently, and that the category of unexplained aerial phenomena is not fixed. The radio silence of the universe, the fact that 60 years of listening have produced no confirmed signal from another civilization, is often described as the most important negative result in the history of science. In most scientific fields, negative results, experiments that found nothing, are less interesting than positive ones. In SETI, the absence of a signal is itself information. It tells us something about the distribution of technological civilizations, about their broadcasting habits, about their lifetimes, about the effectiveness of the methods we are using to search for them. The constraints from the current non-detection are weaker than they might seem, because the fraction of the relevant parameter space that has been covered is still very small. But as the telescopes get larger and the search is more comprehensive, the non-detection becomes increasingly informative. If the next generation of SETI observations using the Square Kilometre Array and other planned facilities surveys millions of nearby stars across a wide range of frequencies and signal types without detecting anything, the implications will be significant. Either technological civilizations are very rare, perhaps we are alone in the galaxy, or they do not broadcast in the ways we are looking for, or they self-destruct before making their presence detectable at cosmic distances. Each of these possibilities has profound implications. The non-detection of extraterrestrial intelligence would, paradoxically, be one of the most important findings in the history of science. The imagery of science fiction about first contact, the way we imagine the moment when humanity discovers it is not alone, reveals something about our anxieties and hopes as a species. The War of the Worlds, H.G. Wells's 1898 novel of Martian invasion, reflected the anxieties of a colonial era about conquest and displacement. The Martians do to humanity what Europe was doing to the rest of the world, with a technology so superior that resistance is impossible until a mundane biological accident saves us. Contact, Carl Sagan's 1985 novel and its 1997 film adaptation, imagined a first contact scenario centered on communication rather than encounter. A radio signal from Vega, a mathematical primer, the slow decoding of instructions for building a machine of unknown purpose. Arrival, the 2016 film based on Ted Chiang's Story of Your Life, explored the language and time perception of non-human intelligence in ways that challenged assumptions about the structure of communication itself. Each of these fictional engagements with the first contact scenario explores different aspects of what such an encounter would mean. The Wellsian tradition explores power and vulnerability. The Saganesque tradition explores communication and shared mathematics as a universal language. The Chiang-Villeneuve tradition explores the possibility of radically different cognition, of minds that perceive time and causality in ways incommensurable with our own. These are not mere entertainment. They are thought experiments that have influenced how scientists and policymakers think about the real possibility they are trying to address. The rate of discovery in astrobiology and exoplanet science has accelerated to the point where it is genuinely difficult to keep track of every significant finding. In 2022 alone, JWST released its first science results demonstrating unprecedented clarity in the study of distant galaxies, exoplanet atmospheres, and objects in our own solar system. The Perseverance rover collected its first rock samples from Jezero crater on Mars and began caching them for eventual return to Earth. Multiple teams published research on the habitability of TRAPPIST-1 planets. New analysis of Enceladus plume data raised the estimated energy output of its hydrothermal system. A new survey of nearby stars found several additional potentially habitable zone rocky planet candidates. The accumulated rate of discovery in this field means that the picture available to scientists today is dramatically different from the one available a decade ago, and the picture available a decade from now will be dramatically different again. The broad trajectory is toward more data, better data, and a slowly narrowing range of uncertainty about the fundamental question: how common is life in the universe? The answer is not yet known, but it will be better known in 10 years and significantly better known in 20, and the generation alive today will likely see results from planetary and astronomical observations that push this question from speculation to data in ways that have never before been possible. The personal testimonies of astronomers and scientists who have spent their careers working on questions related to life in the universe often contain a quality of wonder that is distinct from the more careful public communications of their professional work. Carl Sagan, who was perhaps the most effective communicator of cosmic perspective of the 20th century, described the emotional impact of understanding one's place in the cosmos as a source of comfort rather than insignificance. "We are part of the universe becoming aware of itself," he wrote, "the universe's way of knowing itself." Jill Tarter, the astronomer who spent most of her career at the SETI Institute and was the inspiration for the protagonist of Sagan's novel Contact, has described the experience of listening to the sky for signals from other intelligence as the most hopeful thing she can imagine doing. Not because she expects to hear something on any given night, but because the act of listening is an expression of the conviction that we are not alone and that conviction itself is worth sustaining. Sarah Seeger, the MIT planetary scientist, who has dedicated her career to finding Earth-like exoplanets and characterizing their atmospheres, has spoken about her personal motivation in terms of the deep human desire to know whether there is anyone else out there, a desire she considers as fundamental as any other aspect of the human condition. These personal dimensions of the search for life beyond Earth are not separate from the science. They are part of what drives it, what sustains it through decades of non-detection, and what will ensure that it continues until an answer is found. The question of what any confirmed detection of extraterrestrial life would do to human religion and theology is one that a small but serious group of scholars, theologians, philosophers, and scientists have thought about carefully. The Vatican Observatory, one of the oldest astronomical research institutions in the world and still actively engaged in modern astrophysics, has hosted multiple conferences on the theological implications of life beyond Earth, and its scientists have repeatedly stated that the discovery of extraterrestrial life, even intelligent life, would not conflict with Christian theology in any fundamental way. The Jesuit astronomer Guy Consolmagno has written that such a discovery would be wonderful news, that it would expand our understanding of God's creation rather than diminish it. The Islamic theological tradition has generally been open to the possibility of life elsewhere in the universe, with several Quranic verses interpreted as consistent with other inhabited worlds. Buddhist and Hindu traditions, with their cosmologies encompassing multiple worlds and multiple planes of existence, have perhaps the least adjustment to make to the discovery of other inhabited worlds. The most challenging theological implications would be for traditions that place strong emphasis on the unique status of humanity and the specific historical events of one planet's religious history. How these traditions would respond to the discovery of intelligent life elsewhere, whether they would seek to evangelize, to draw parallels, or to radically revise their frameworks, is genuinely unknown. It is a conversation that has barely begun and that will need to accelerate as the probability of such a discovery increases. The specific physical properties that make Earth hospitable to life, the presence of liquid water, a stable climate, plate tectonics recycling carbon, a magnetic field shielding the surface from cosmic radiation, a large moon stabilizing the axial tilt, a gas giant in the outer solar system deflecting potential impactors, have been studied carefully to determine how common this combination might be. The rare Earth hypothesis, articulated by Peter Ward and Joe Brownlee in their 2000 book of the same name, argued that the specific combination of circumstances required to produce a habitable world like Earth was extraordinarily unlikely, and that complex animal life might be unique to Earth or nearly so in the galaxy. This position has been challenged on multiple grounds over the subsequent 2 decades. The assumption that complex life requires all the specific conditions of Earth has been weakened by the discovery of complex ecosystems in deep-sea hydrothermal vents, under Antarctic ice, and in other extreme environments. The assumption that a large stabilizing moon is necessary for a stable axial tilt has been questioned by climate models, showing that some Earth-like planets can maintain stable climates without a large moon. The assumption that plate tectonics is necessary for long-term habitability is challenged by modeling showing alternative carbon recycling mechanisms. None of this definitively refutes the rare Earth argument. It may still be that the specific configuration of circumstances on Earth is unusually rare, but it suggests that the minimum requirements for habitable worlds are less stringent than the most pessimistic versions of the hypothesis claimed. The debate continues to drive productive scientific work. The history of humanity's changing understanding of our position in the cosmos is one of the great intellectual journeys of civilization, and each stage of that journey has involved accepting a larger and stranger universe than previously imagined. The ancient geocentric cosmology placed Earth at the center of a modest collection of celestial spheres. The Copernican revolution moved Earth to a position orbiting the Sun. The recognition that the Sun was one ordinary star among many moved our location from the center of the cosmos to an undistinguished point in a spiral galaxy. The 20th century discovery that the Milky Way is one of billions of galaxies extended the scale of the known universe by orders of magnitude. The recognition that the observable universe, everything within the horizon set by the age of the universe and the speed of light, may be only a small fraction of what exists, and that the broader universe may contain regions with different physical laws, extends the scale further still. Each of these transitions was psychologically challenging. They required giving up a cherished centrality, a specialness, a sense of being at the focus of cosmic attention. And yet each transition was also liberating. It expanded the scope of what could exist, what could be known, what the universe could contain. The next step in this journey, and the discovery that life exists beyond Earth, would be the most profound of all, transforming us from the only known example of life to one of many, from a cosmic anomaly to a natural phenomenon. It would be, in the deepest sense, a discovery about our own nature, that what we are is not exceptional but universal. The instruments of the coming decades will be genuinely transformative in their capabilities. The extremely large telescope currently under construction on Cerro Armazones in the Atacama Desert of Chile will have a primary mirror 39 meters in diameter, more than 4 times the diameter of any existing optical telescope. Its light-gathering power and angular resolution will make it capable of directly imaging Earth-like planets around nearby stars and analyzing their atmospheric spectra with enough detail to search for biosignature gases. The same facility's adaptive optic systems will correct for the distorting effect of Earth's atmosphere in real time, achieving image sharpness comparable to the Hubble Space Telescope, but with vastly more light-gathering power. The square-kilometer array, with its dispersed network of thousands of radio receivers spread across thousands of kilometers in South Africa and Australia, will have a collecting area equivalent to a radio dish a kilometer across, and will be sensitive to radio signals 100 times fainter than anything detectable today. Its SETI search capabilities are being designed in as part of its core science program, reflecting the shift in the scientific community's attitude toward the legitimacy of this research. The combination of these ground-based facilities with space-based observatories, the successors to JWST currently in planning stages, designed specifically to characterize exoplanet atmospheres, means that the 2030s and 2040s will see a genuine qualitative leap in our ability to assess whether any nearby planet shows signs of life. The outcome of that assessment is not predictable, but the assessment itself will happen. The sheer variety of environments in which life might exist, the conceptual space of possible biochemistries, possible energy sources, possible information storage molecules, has been approached through two very different methodologies. The first is theoretical, starting from first principles of chemistry and physics, asking what combinations of molecules could, in principle, support self-replication and evolution under what physical conditions. This approach has generated a rich literature on alternative biochemistries, from silicon-based life to life in liquid ammonia or liquid methane, and has consistently found that carbon-based, water-mediated chemistry is probably the most versatile and efficient option under the widest range of conditions, while not excluding alternatives in specific environments. The second methodology is empirical, studying the actual diversity of life on Earth in extreme environments and asking what the physical and chemical limits of Earth life actually are. This approach, driven by the explosion of extremophile research over the last 3 decades, has consistently pushed the known boundaries of life further than expected. The lower temperature limit for active metabolism is now approximately -20 degrees Celsius, achieved by certain Antarctic microorganisms. The upper limit for active metabolism is approximately 120 degrees Celsius, achieved by certain hyperthermophilic archaea living in deep-sea hydrothermal systems. Organisms have been found living at pressures of more than 1,000 atmospheres in the Mariana Trench. Others survive extreme desiccation, extreme salinity, extreme acidity and alkalinity, and radiation doses that would be lethal to most terrestrial organisms. The envelope of conditions under which life exists on Earth is far wider than was known even 20 years ago, and each extension of that envelope increases the plausible range of habitats elsewhere in the universe. The sociological and institutional history of how the scientific community has engaged with the UAP topic is itself illuminating. For most of the period from 1969 to 2017, the tacit consensus in mainstream science was that UAP were not a legitimate research topic, that the available evidence was of insufficient quality, and that association with the topic carried reputational risk that made it rational for serious scientists to avoid it. This consensus was self-reinforcing. The absence of serious scientific attention meant that the quality of data collection and analysis in the field was low, which confirmed the impression that nothing rigorous was happening, which maintained the low status of the topic. The 2017 New York Times article and the subsequent congressional hearings broke this cycle by providing credible, authenticated data from military sources that could not be easily dismissed. The shift has been gradual but real. NASA established a UAP study group that reported in 2023, recommending that NASA take a systematic scientific approach to UAP data collection and analysis. Congress mandated the establishment of the All-Domain Anomaly Resolution Office to investigate UAP across all military services and intelligence agencies. Multiple peer-reviewed scientific papers on UAP have been published in mainstream journals, a rarity before 2019. The Galileo project at Harvard has adopted a systematic scientific methodology. The arc of institutional change has been from dismissal to grudging acknowledgement to active engagement over approximately 6 years, remarkably fast by the standards of scientific culture change. Whether this engagement will produce significant findings is unknown, but the shift from dismissal to investigation is itself a significant development. The night sky, as experienced by humans before the invention of artificial lighting, was a profoundly different sensory experience from what most people living in modern cities know. Light pollution now means that more than a third of humanity cannot see the Milky Way with the naked eye, and in the most densely populated parts of the world, the sky never truly darkens. The experience of a truly dark sky, the sky visible from remote deserts, from high mountains, from the open ocean, is qualitatively different from anything most urban dwellers encounter. The Milky Way appears not as the faint smear visible from suburbs, but as a blazing river of light, so dense with stars that the dark rifts within it, absorption nebulae blocking the more distant stars, are as visually striking as the stars themselves. Under a truly dark sky, the Andromeda Galaxy is visible to the naked eye as a faint, elongated patch of light. On very clear nights, other galaxies and star clusters become visible that are simply invisible from light-polluted skies. The experience of standing under this sky, knowing that each of those points of light is a sun that most of them have planets, that some of those planets may harbor life, that the light you are seeing left those stars decades or centuries or millennia ago, carries an emotional weight that no amount of reading about astronomy can replicate. The astronomers who chose their careers under dark skies, who made the initial decision to spend their lives investigating the universe by standing beneath it and looking up, made that decision partly from this visceral experience. The sky has always been an invitation. It remains one. The long history of reported encounters between humans and entities not recognized as human, encounters described in religious, mythological, folkloric, and more recently UAP contexts, shares certain structural features that have fascinated anthropologists and psychologists. The beings described are often smaller than humans, often luminous or associated with light, often described as conveying information or knowledge, often perceived in altered states of consciousness or at boundaries between waking and sleep. The anthropologist Michael Harner, who spent decades studying shamanic traditions across multiple cultures, documented a remarkably consistent set of encounters with non-human entities in shamanic journeys that share features with modern alien encounter narratives. The psychiatrist John Mack of Harvard Medical School spent the last decade of his life interviewing people who reported alien abduction experiences and concluded that while he could not determine the literal reality of the reported events, the experiences themselves were not simply hallucinations or fabrications. They had a quality of reality and a consistency of detail that deserved serious phenomenological attention. His work was deeply controversial and cost him significant professional standing, but the seriousness with which he approached witness testimony and his refusal to dismiss it simply because it did not fit conventional frameworks exemplifies a thoughtful middle position that neither credulously accepts extraordinary claims nor dismissively denies the reality of unusual experiences. Whatever these encounters ultimately are, whether literal contacts with non-human intelligence, complex psychological events, cultural elaborations of deeper archetypes, or some combination, they represent a significant and consistent strand of human experience across many cultures and many centuries that deserves more rigorous attention than it typically receives. The question of what it would actually feel like to live in a world where the existence of extraterrestrial life had been confirmed, where the fact of other inhabited worlds was as established and unremarkable as the existence of other continents, is one that imagination can approach but not fully enter. The generation alive at the moment of confirmation, if that moment comes, will experience a before and after that no previous generation has known. The confirmation of microbial life in a Martian rock sample, or in an Enceladus plume, or in the atmospheric spectrum of a nearby exoplanet, would be a discovery whose implications would unfold over decades and centuries rather than being absorbed in a single moment. The initial announcement would be extraordinary, but the actual transformation of human self-understanding would be gradual as the implications work their way through philosophy, religion, art, and daily life. Whether that transformation would be primarily reassuring, we are not alone, the universe is alive, or primarily unsettling, our uniqueness was an illusion, our religions may need revision, probably depends on the nature of the discovery and on the cultural moment in which it occurs. What seems certain is that the confirmation would be irreversible. You cannot unlearn that life exists elsewhere. And once that knowledge is part of the human inheritance, everything that follows, every question we ask about ourselves and our place in the cosmos, would be asked from a different position than we now occupy. The sky above would look the same. What it would mean would be transformed. The specific question of whether any unidentified aerial phenomena observed by military and civilian witnesses represent technology from a non-human source, whether extraterrestrial or of some other origin, cannot currently be answered from the available evidence, and responsible researchers in the field say so clearly. What can be said is that the quality and quantity of evidence for genuinely anomalous aerial phenomena has improved substantially over the last decade, that the scientific and governmental communities have shifted from dismissal to investigation, and that the investigation is still in its early stages. The transition from a situation in which trained military observers felt unable to report unusual observations for fear of ridicule to a situation in which official protocols exist for reporting and investigating them is itself significant. The data being collected now from the All-Domain Anomaly Resolution Office, from the Galileo Project's automated sensors, from the expanded SETI programs, will be substantially more rigorous and more interpretable than the anecdotal record of the previous 70 years. Whatever the phenomenon turns out to be, the tools now being brought to bear on it are appropriate for the task. Whether that will produce extraordinary findings or prosaic explanations, better imaging revealing conventional aircraft atmospheric phenomena or adversary technology, remains to be seen. The honest position is one of sustained, curious, open attention. Something anomalous appears to be happening in our skies, often enough to be documented systematically, and the most rational response is to document it carefully and follow the evidence wherever it leads. The universe is not only vast in space, but vast in time, and this temporal vastness has implications for the question of life that are worth sitting with as the night deepens around you. The universe has been running for approximately 13.8 billion years. Earth formed approximately 4.5 billion years ago. Life appeared on Earth within a few 100 million years of it becoming habitable. Complex multicellular life appeared approximately 600 million years ago. Anatomically, modern humans appeared approximately 300,000 years ago. Writing, the technology that makes the accumulation and transmission of knowledge possible across generations, was invented approximately 5,000 years ago. Radio technology, the tool that first allowed us to begin detecting other civilizations, if any exist, was developed approximately 150 years ago. We are extraordinarily recent. Our technological civilization is a thin layer on the geological record, a flash of activity in a planet that has existed for 4.5 billion years and a universe that has existed for 13.8 billion. If there are other civilizations out there, some of them are likely billions of years older than ours, which implies capabilities, knowledge, and possibly perspectives so different from anything we can currently imagine that our very category of civilization may not adequately describe what they have become. The humility that comes from this temporal perspective is not diminishing. It is expansive. It is an invitation to wonder at what 13.8 billion years of cosmic evolution might have produced in the darkened spaces between the stars. The cultural impact of the possibility of alien life, regardless of whether it exists, has been profound and continues to be so. Science fiction, from its earliest pulp magazine manifestations through its golden age in the mid-20th century and into its contemporary forms in film, television, and literature, has served as a laboratory for exploring the implications of contact with other intelligence. The best science fiction in this tradition does not ask simply whether aliens exist, but what it would mean for human identity, for religion, for politics, for our understanding of consciousness. If they do, Arthur C. Clarke's Childhood's End, Ted Chiang's Story of Your Life, Stanislaw Lem's Solaris, and Ursula K. Le Guin's Hainish Cycle all explore aspects of this question with a seriousness and philosophical depth that matches anything in academic philosophy or science. The scenario of first contact, the moment at which humanity discovers that it is not alone, has been the premise for an enormous quantity of creative and philosophical work, precisely because the implications are so large and so uncertain. Every religious tradition on Earth would need to reckon with what the existence of other intelligent beings means for its specific cosmological framework. Every political system would need to reckon with the implications for human self-governance. Every understanding of human uniqueness and human dignity would need revision. These are not trivial questions, and the fact that we are now, for the first time in history, developing the scientific tools to potentially answer the foundational factual question that underlies them is one of the most significant things about the period we are living through. The pace of discovery in exoplanet science, astrobiology, and UAP research has accelerated in recent years and shows no sign of slowing. The next decade will see the arrival of the Europa Clipper at Jupiter's moon, the landing of the Dragonfly rotorcraft on Titan, the ongoing accumulation of JWST atmospheric data, on rocky exoplanets, the sample return mission bringing Perseverance's Martian rocks to Earth, and the continued expansion of CT observations under Breakthrough Listen. Ground-based astronomy will see the completion of the extremely large telescope, the 30-meter telescope, and the giant Magellan telescope, 3 optical and infrared observatories with light-collecting areas far exceeding any existing telescope, capable of directly imaging nearby exoplanets and analyzing their atmospheres with unprecedented sensitivity. The Vera Rubin Observatory, currently under construction in Chile, will survey the entire southern sky every few nights, detecting anything that changes or moves, a capability that will discover an enormous number of new solar system objects and potentially detect the signatures of alien megastructures if any exist within range. The square-kilometre array under construction in South Africa and Australia will be the world's largest radio telescope and will dramatically expand CT capabilities. The question of whether we are alone in the universe has never been closer to being answerable by empirical means. The answer, when it comes, will be one of the most significant pieces of knowledge our species has ever acquired. In the quiet of this particular moment, and wherever you are, whatever time it is, the sky above you is carrying something, light from stars thousands of light years away, that left those stars before recorded history began. Cosmic microwave background radiation that last interacted with matter 380,000 years after the Big Bang, when the universe was 100 times smaller than it is today. Radio waves from the first generation of radio broadcasting, now spreading outward in an expanding sphere that has so far reached approximately 100 of the billions of stars in the galaxy, and perhaps traveling in directions we have not yet learned to listen to, signals of some other kind from some other world that is also old enough and curious enough to wonder if it is alone. The universe is ancient and vast beyond any comfortable intuition. It has been running its chemistry and its physics for nearly 14 billion years across a volume containing more stars than there are grains of sand on Earth. That chemistry includes, in at least one instance, the emergence of life, the development of consciousness, and the formation of a species capable of looking up at the sky that made it and asking the question, is there anyone else? Whether the answer is yes or no, the question itself is one of the most extraordinary things in the known universe. A small arrangement of matter on a small rock orbiting an ordinary star, generating the awareness needed to ask about its own context. However the story of life in the universe turns out, that moment of asking is worth holding gently in the quiet before sleep, as the light of those 2 trillion galaxies falls silently on the world outside your window. Sleep well.